Okay, so let's go ahead and get started. So I'm going to go through a couple of the problems that we did in recitation today over Gauss's law, and then I'm going to talk a little bit about the stuff that we're going to be doing tomorrow when it comes to capacitors. So the first problem that I want to do is the one with this cylinder, because I haven't done any of these ones yet. So we're told that we have some cylinder with some radius of A, and what we want to do is we want to find what the electric potential is at some distance h, or the difference in electric potential between the axis. So we want to find delta V is equal to V at h minus V at 0, which is equal to the integral of E dot dl from 0 to h. We're also told that this has some total length of L, I believe, and then there's some charge Q that's evenly spread over, oh, I'm frozen? Okay, let me fix that. If it's not one thing, it's always something else. Okay, yeah, that should be good now. Okay, okay. And let me just check to make sure that this is exactly the problem this as written here. So exam 1, exam 2, 2007. So yeah, just so this is exactly the same. This is some A. This is some B. And this is some capital L. Okay. 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 And what it actually says is that this is this point B is actually equal to 5 times A. Okay. So in order to solve this one, the first thing that we need to do is we need to find what the electric field is everywhere. Because in order to calculate what the difference in electric potential is, we're going to need to know what the electric field is. And so in order to do that, the first thing that we can do is we can say that there are two regions we need to find the electric field for R is less than A and R is greater than A. So when we do this, we're going to be applying Gauss's law, and so that's to say that the integral of E dot ds is equal to Qn divided by epsilon naught. Because this is cylindrically symmetric, that's going to say that the Gaussian surfaces that I want to draw are these cylinders, where the axis of the cylinder of charge is going to be the same axis for the Gaussian cylinder. So that's to say, if this is some lowercase l, then the integral of E dot ds is going to reduce so that this is going to be equal to E times s, and then this is going to be equal to E times 2 pi R times L. Okay. So then the next thing that we want to do is look at these regions and then figure out what Q in is. So in general, Q in is going to be equal to the integral of rho dV. And so we need to figure out what rho is. So I tell you that there's some total charge Q evenly spread throughout this cylinder. And that's just to say then that rho is going to be equal to the total charge divided by the total volume that it's going to be spread over. And so this has some radius A, and so this is going to be pi A squared times the total length, capital L. Okay. So now we have almost everything that we need to find what R is less than, what the electric field is for R is less than A. We just need to figure out what Q in is. So Q in is going to be equal to the integral of rho, which is going to be Q divided by pi A squared L, times dV. In this case, dV is going to be equal to 2 pi R times lowercase l times dr. So this is 2 pi R L dr. Okay. So then this has some radius of R, and so that means that the limits of integration that I'm going to have are going to go from 0 to R. Right. So this is that important point that I keep mentioning, that the electric field, when we're inside the the conductor, when we're trying to find what the what Qn is, the limits of integration are going to go from whatever the lower bound is. In this case, it's 0 up to R on the inside. Okay. So when we do this, what we end up seeing is that Qn is going to be equal to my factors of pi cancel. This is the 2 is going to cancel because I get an R squared divided by 2, and then this is going to be equal to QL R squared over A squared L. Okay. So now, what we want to do is we want to combine this with the left-hand side of Gauss's law, and then what we see in the end is that this electric field is going to be equal to, my L's are going to cancel. I'm going to have an epsilon naught in the denominator now, so this is going to be 1 over 2 pi A squared L times R, and there's a Q here and an epsilon naught as well. Okay, let me just check that real fast. 2 pi R A squared L epsilon naught. Yeah. Right. So this is my electric field for R is less than N. Okay. Now what we want to do is we want to find what the electric field is for R is greater than N. And really, the only thing that's going to change is what my limits of integration are, because now this is my Gaussian surface. So my limits of integration are going to go up to the radius of A. And so what that does is that changes this here. So for R is greater than A, Qn is going to be equal to really the same thing here, only instead of an R, I'm going to have an A, so those are going to cancel. And so this is going to be QL divided by L. We can plug that into the rest of Gauss's law once we solve for E, and what we end up seeing there for R is greater than A. E vector is going to be equal to Q divided by 2 pi epsilon naught L R times R hat. Okay. So, not too bad. Any questions about what I've done so far? I'll give you guys a second to look at this and ask me any questions if you have them. Okay, so now that we have our electric field, we want to find the difference in electric potential between 0 and 5A. Okay. So in order to do that, what we need to do is we need to realize that we have two different electric fields here. So to integrate from 0 to H is what I have here now. Really, this is going to be our 5A. In order to evaluate this integral, we need to break it up into two pieces. And so that's going to be to say I have one integral that goes from 0 to A, and a second integral that goes from from A to 5A. Okay. So that's going to say that this is going to be equal to the negative integral of E1 dot dl minus the integral of E2 dot dl. This one goes from 0 to A. This one goes from A to 5A. Okay. And then we just need to plug in what our electric fields are and then just evaluate this. So this is going to say that this one is going to be, I'm just going to factor out everything that's a constant. So this is going to be minus Q divided by 2 pi A squared L epsilon naught. The dot product here is going to go away because dl vector is going to be equal to r hat dr. And so r hat dot r hat is 1. And so this is going to be the integral of r dr from 0 to A. Minus, this is going to be Q divided by 2 pi epsilon naught L, the integral from A to 5A of dr over r. Okay. So now we can evaluate these integrals. These are pretty straightforward. This one's just going to give me r squared divided by 2, and so that's going to be minus Q. I'm actually, did I lose something here? No, I didn't. It's fine. It's fine. This is going to be minus Q divided by 4 pi A squared L epsilon naught times A squared. Minus Q divided by 2 pi epsilon naught L times the natural log of, really this is the natural log of 5a minus natural log of a. And so when I have a difference of natural logs, there's a rule that says that if I have the natural log of a minus natural log of b, this is going to be equal to ln of a divided by b. And so that allows me to bring these two together, and so then what I see in the end is this term right here is going to be a natural log of 5. Okay, and that's it. So this is a pretty common type of question that I might ask you, because it requires you to do two things. One is to find what the electric field is due to the distribution of charge, and the second is to find the potential difference between 2 points. And the reason why these calculations of finding electric potential differences are important is because when we get into capacitors, we're going to see that if you've done the homework already, you'll know that the definition of capacitance is going to be the charge per the change in electric potential. And really what a change in electric potential is akin to an electrical, or in a circuit, is the voltage. So calculating changes in electric potential are going to be very important when we get to circuit analysis. And so this is kind of building up to that in terms of being able to find electric fields and then using those electric fields to find differences in electric potential, which again is akin to the voltage. Okay, so I'll give you guys a second to look at this and let me know if you have any questions. Can you do an example of a planar type? Yeah, I'll do a planar example too. Okay, yeah, because the planar symmetry, in some ways it's easier, and sometimes in some ways it's not. And I'll explain why that is, and it has to do with the way that you choose where to put the Gaussian surface. So let's look at an example of that. So if I remember correctly, it was actually one of those in recitation today, and I'll try to do that exact same problem. So this tells you that you have some slab of charge. I lost my chart. I have some slab of charge that has some charge density, constant charge density rho. So here's our slab of charge, and this is going to be a very large slab of charge, infinite in the plane. So, and that's important because in order to apply Gauss's law, what you really need to do is you need to say that the electric field is going to be pointing in this direction, right? And so if this wasn't an infinitely large slab, then on the ends the electric field would do something like this, and then applying Gauss's law is very difficult. So that's why it's important to say that these are infinitely large. So we say that this has some thickness of t, and I'm actually going to draw this again so that I can make it bigger to draw my Gaussian surface. So it's going to have some thickness of t, and then this is just going to go off like that. Okay. So this is the thickness of t that this has. This has some charge density rho that's evenly spread throughout. And what we want to do is we want to find what the electric field is everywhere. So in order to do that, we have to be very careful with the way that we choose our Gaussian surface. And a trick to doing these problems with these planar symmetries, when I have some slab that has some thickness, is to consider the point exactly, the plane that's exactly in the middle of this. And the reason why I want to consider this plane is that for every point on this plane, the electric field is equal to 0. Because if this is uniformly spread, I have the same exact amount of charge and distribution of charge on this side as on this side, and so the electric field that's produced by those two pieces is going to cancel in the middle. And so the reason why I want to do that is because now when I draw my Gaussian surface, I have three, and let me just shade this in all the way. I have three surfaces that I need to consider. I have the side, I have this surface that's at the middle, and the side that's on this side. So writing down Gauss's law, I know that I need to find the flux out of the entire closed surface. And so really that means that it's the sum of the flux through all three of the surfaces here. So this is the left, the right, and then the sides. But the reason why I chose to put this exactly where I did is because the electric field at this point is going to be zero. The flux through this side is zero. So what that allows me to do is to say if this has some surface area of A on the right face, then this integral of E dot ds is just going to be E times A. The flux out of the sides is zero because of the dot product. We only have the flux through this one. Okay. So now to determine what Qn is, we say that Qn, as always for insulators, is going to be equal to the integral of rho dV. And then we just need to parameterize what dV is going to be. So in order to find dV, what we can say is that there's some infinitesimal distance dx here. And so dV is just going to be equal to A dx, right? Because this makes a volume element. It's an area times an infinitesimal length. And so that's going to give me what dV is. Okay. So now to find what Qn is, we do the same thing that we always do. We can plug this in here. We can say that this is Qn is equal to the integral of rho, which I just say is some constant. Let's call it rho 0. Rho 0 A dx. And my limits of integration here are going to go from 0, which is where I'm defining the center. So the center is going to be 0, to some variable distance x. Okay. So when we do this integral, we end up seeing that this is going to be rho 0 A times x. And we already have what the left-hand side of Gauss's law is, and so we can put this together to say that E vector is going to be equal to, this is going to be rho 0 x divided by epsilon naught in the x hat direction. And that's actually it for the portion that's inside. Okay. The next thing that we want to do is we want to find what the flux is, or what the electric field is outside. And so to do that, we draw a similar surface, but now the surface is going to go, it's going to extend past the boundary of the charge distribution. And so when we do that, again, everything here is almost the same except for the limits of integration. So now I'm not going up to this variable distance x while I'm still inside the slab. I'm going to go up to the boundary of the slab. And if this is a total distance of t, then this distance is going to be t divided by 2. And so when I do that, what I end up seeing is that this Qn, rather than being rho 0 A times x, this is going to be rho 0 A times t divided by 2. And then the second electric field is just going to be E vector is going to be equal to, this is going to be equal to rho 0 t divided by 2 epsilon naught. Okay. And that's it for the planar case. So I'll let you guys digest this, and then I'll move on to another one. So we've done so far the cylindrical symmetry, the planar symmetry. So let's do a spherical symmetry problem for completeness, and then I'll move on and talk about what we're going to be doing tomorrow and some of the things that you will see on the homework. So the example that I want to do for this one, again, was a question from one of the old exams. So I have some Q that's evenly spread here. This is some radius A. This is some thickness of T. And then there's some point H on the outside here. And what I want to do is I want to find delta V is going to be equal to V at H minus V at 0. Okay. So in order to do this, we need to consider three regions. The region where R is less than A, the region where R is greater than A, R is greater than A and less than A plus T, and the region where R is greater than A plus T. Okay. Now, for this problem, the charge is evenly spread over the insulating shell that I have here. And so what that means is when I draw my Gaussian surface for R is less than A, the charge that's inside that Gaussian surface is going to be 0. And because that charge inside the Gaussian surface is going to be 0, that also says that the electric field is equal to 0. Okay, so the first one's down, so that's nice. So the second one that we need to look at is the one that goes in this region, so between A and A plus T. And so in order to do this one, we'll have to evaluate Gauss's law. So integral E dot dx is equal to Qn divided by epsilon naught. This is going to reduce to E times S, which is going to be equal to E times 4 pi R squared. Now, we'll have to find what Qn is, and this is probably the trickiest part of this problem, just finding what Qn is. So this is going to be equal to the integral of rho dV, but we need to find what rho is. Rho is going to be the total charge divided by the total volume, and so this is the charge Q divided by 4/3 pi times A plus T quantity cubed minus A cubed. Okay, and the way that you can see that this is the volume that I want here is to consider if I didn't have this hollow piece taken out and it was just a solid insulator, then the volume of that would be the 4/3 pi times A plus T cubed. We're frozen. Technology, why does it do things like this? Okay, how far did I get? I didn't get much farther forward. Okay. Yep. Okay. So I'm just talking about the charge density here and why it is the way that it is. So this is going to be the 4/3 pi times quantity A plus T cubed minus A cubed. Because if this was solid and it wasn't hollow, then the total volume would be the 4/3 pi quantity A plus T cubed. But we're taking out this portion in the middle that itself has a volume of 4/3 pi A cubed. And so that's why this is the quantity A plus T cubed minus A cubed. Okay. So now that we have what rho is, we're ready to find what Qn is. So we need dV here. So dV is going to be equal to 4 pi r squared dr for spherical coordinates. We can plug in what rho is, and since it's a constant, I'll bring it on the outside. So this is going to be Q divided by 4/3 pi times A plus T cubed minus A cubed times the integral of 4 pi r squared dr. And now we just need to plug in our limits of integration. So here, the charge distribution is going to start at A, so our lower bound is going to be A, and our upper bound is going to be the variable radius R. Okay? So this is going to be R, because this is the furthest that the charge distribution goes. It goes up to the edge of the Gaussian surface when I'm on the inside, and so that's just going to be the variable distance or radius R. So when I do this integral, what I'm going to end up finding is that this is going to give me a 4 pi over 3, which is going to cancel the one that I have here. And then I'm going to have r cubed minus a cubed. So Qn in this case is going to be Q times r cubed minus a cubed divided by, divided by a plus t quantity cubed minus a cubed. Okay, so that's what our Qn is. And so we can put this together with the left-hand side of Gauss's law, and what we see in this case right here is that the electric field is going to be equal to 1 over 4 pi epsilon naught, and we'll put our r squared there, times, and we can put q up here. This is going to be r cubed minus a cubed divided by a plus t cubed minus a cubed in the r hat direction. So that's our electric field in this case. And you could simplify this more if you wanted, if you divide this r squared through this and this. Okay, so now we want to find the electric field in the region where r is greater than a plus t. And in this case, we could do the integral here where we would be integrating from a to a plus t, or we could realize that when I have this Gaussian surface here, I'm just enclosing the total charge that I have spread on here, which is q. And so that means that for this Gaussian surface in this region, that q in is just going to be equal to capital Q. And when I plug that in and use the left-hand side of Gauss's law, what I end up seeing is that E vector is going to be equal to 1 over 4 pi epsilon naught q divided by r squared times r hat. Okay? Which is itself an interesting result because, so I had a question. With a sphere, can you add the conductor surrounding the insulator? I'm still not solid on the. Okay, yeah, I can do one with a conductor after this. So this one, this electric field that I have here is actually, when we look at it, just the electric field of a point charge. And what that tells you is something that's kind of interesting, that once you're outside this region, I don't really care what the distribution of charge was, as long as it was spherically symmetric. The electric field is just going to resemble the electric field from a point charge. Okay. So now, in order to define what the difference in electric potential is between 0 and h, what we do is we do essentially the same thing that we did in the last, or the problem with the cylinder. And that's we can write this as the integral of E dot dl from 0 to h. But because we have these three regions, we have the integral from 0 to a, E1 dot dl, minus the integral from a to a plus t of E2 dot dl, minus the integral from a plus t to h of E3 dot dl. And something that we notice here right away has to do with the first integral. This one's just going to be 0 because the electric field in this region is going to be 0. And because we're not quite short on time, but I want to move on to other things and not spend too much time just doing calculations. You can see that in order to evaluate this, I'm just going to take this and plug it in here, and then this and plug it in here, and then it's just a matter of evaluating the integral. Okay. So let's talk about some problems with conductors. So, and again, let me pause here and see if anybody has any questions before I move on. Yeah, apple juice. So let's do a problem with conductors. So I'll just make one up off the top of my head. So this is something that you guys can do too to practice these. Just play around with different charges that you'd want to put on it, and then make sure that you're getting the results that are consistent with your expectations. So I'm going to say that I have some charge of plus 5q at the origin. I have a conducting shell that has some inner radius of A, some outer radius of B, and I'm going to put some charge minus 3q on the conducting shell, And what I want to do is I want to find first what the electric field is everywhere, and second what the surface charge density at A and B are. We could additionally find what the difference in electric potential is between some points here. So we could say between the point A over 2 and 2B, but that's just another calculation that follows exactly the same process and logic that we've already done. So for this one, we're going to have three regions. So R is going to be less than A, R is greater than A. I always do this backwards. R is greater than A and less than B. R is greater than B. Okay. So for the region R is less than A, our Gaussian surface is going to look like this. We know from doing a lot of these that interval E dot ds is going to be equal to Qn divided by epsilon naught. And so the interval of E dot ds is just going to be E times 4 pi r squared, as it always is for spherical symmetry. Qn is just the charge 5q that's on the inside here. And so when we put that together with the left-hand side of Gauss's law, what we end up saying is that E vector is going to be equal to 1 over 4 pi epsilon naught times 5q divided by r squared times r hat. Okay. Now the region between A and B, so this is the Gaussian surface that I want to draw here. When I draw this Gaussian surface, I'm on the inside of the conductor, and we know that by definition, inside perfect conductors in static equilibrium, the electric field is going to be equal to 0. The other thing that we can say here is if the electric field is equal to 0, so that says that integral E dot ds is equal to 0, right? Because if E is 0, then this interval is 0. This also says that Qn divided by epsilon naught is 0. And epsilon naught is just a constant, and so what that says is Qn is 0. So what we can say from this is that because Qn is equal to 0, this is also equal to the charge. I mean, by definition, Qn is the charge that's inside the Gaussian surface. But there's only two places that charge can be, because this is a conductor. You can have charge at the center, which is what we have here, the plus 5q. And you can have a charge at the surface, right? Because conductors allow charge to flow, you're always going to only have charge at the surface. And this needs to be such that when I add this QA, the 5q plus the charge at this surface here that goes all the way around is going to be 0. And so what that says is that QA necessarily needs to be minus 5q in order for this to balance, so that the total charge inside is 0. So we found what the charge at the inner surface is going to be, and we found what the electric field on the inside of the conductor is. It's just really by definition 0. The next thing that we can do is we can find what the charge on the outer surface is. And if we wanted to find the surface charge density, sigma A is just going to be equal to this minus 5q divided by the surface area of the conducting shell at its inner radius. And so this is going to be 4 pi a squared. So that would be our surface charge density. Where was I going next? Okay, right. So we can also find what the charge on the outer surface is going to be, because we know that the total charge is going to be equal to the charge at the inner surface, QA, plus the charge at the outer surface, QB. So we know now what QA is. We also know that I put some minus 3Q on the conducting shell. So that's what Q total is. So this is minus 3Q is equal to QA, which is going to be our minus 5Q, plus QB. And so when we rearrange this, what we end up seeing is that QB is going to be equal to just 2Q. Okay? And we can check to see does that make sense. Well, QA is minus 5Q, QB is 2Q. We add it together, we get the minus 3Q. That's the charge on the conductor. Okay. Now, the last thing that we need to do is we need to find what the electric field is in the region R is greater than B. So this is going to say that 4 pi R squared times E is going to be equal to Qn. So here's our Gaussian surface. Qn is just the total charge that's inside here, and so that says that this is going to be the 5Q minus the 3Q on the conductor. So that's going to say that this is going to be 2Q divided by epsilon naught, and so E vector is going to be equal to 1 over 4 pi epsilon naught 2Q divided by R squared times R hat. Okay. So the way that I did this was I said that Qn is just equal to the sum of the charge at the center, so this is going to be the plus 5Q, and the charge on the surface, which is the minus 3Q. So that's how I got this 2Q. But alternatively, what we could have done was we could have added up the charge for every single surface that we had in the origin. So that's to say that this is going to be the plus 5Q plus QA plus QB, which is going to be equal to plus 5Q minus 5Q plus 2Q. These two cancel, and then I'm left with just the 2Q. So there's kind of two different ways to think about that. Okay. So let me know if that clears some things up. I can do another one of these if it doesn't. But really, if I'm doing this in spherical symmetry, the only thing that would really change would be the fact that I would change what this Q and this Q were. I just changed the numbers for those Qs. But the principle is always the same. It's what's the charge that's inside, and the charge on the conductor can only reside at the inner surface and the outer surface. And the electric field is going to be 0 inside the conductor. So that says that if the electric field inside the conductor is 0, Qn has to be 0, and so that's how you can figure out what this QA is. And then if I know that this has some total charge of some amount, in this case this was minus 3Q, that's going to be equal to the charge at the inner surface plus the charge at the outer surface, which is what I said here, and then you can algebraically solve for what the charge is on the outside. Okay. Alright. So, let's see, how are we on time? We got 22 minutes. So, I think what I'm going to do now is I'm actually going to go through some of the stuff on the homework. I mean, I realize that it's all printed in the notes, but it might be helpful for you to see me explain it verbally. So, this is moving into territory where we have applications of all the things that we've been talking about. So you might be wondering, who cares about applying Gauss's law and finding electric fields and differences in electric potential? How is it useful? I personally think it's really cool, and so that should be enough to satiate your curiosity. But what it is really useful for is circuit analysis, and that's what we're going to be getting into for the rest of this week. Actually, everything that we're going to cover up until the test is going to be circuit analysis. So we're going to start with capacitors. The definition of capacitance is going to be the charge divided by some change in electric potential. And so that's to say, if I have some system of conductors, so the example that I give in the notes is I have these two parallel plate capacitors that have some thickness like this. If I have some charge on the system, and I also know what the electric potential is, the capacitance is going to be the ratio of the charge on the system to the difference in electric potential. It's clear. So if the 5Q was from the insulator, that would have been the difference when combining the conductor and the insulator. Yeah. So if the example that I gave. I actually think I might have done something like this in the notes. I don't remember now. But there was a problem like this that I did at some point, or it was one on exam, old exams. What if instead of having the 5q as a point charge, I had the 5q evenly spread over some sphere at the center? I think that's what you're asking about. That doesn't change any of what I'm going to do for the conductor. So the conductor portion is still going to be exactly the same. If this was the plus 5q and then I put the minus 3q here, I would still have a plus minus 5q at the center, or not at the center, but at the inner surface, and a 2q on the outer surface. But what this would change is I'd have to have an additional region where I found the electric field on the inside. So that's what's going to be different. Okay. So coming back over to this definition of capacitance, really what we're trying to get at here is defining some quantity that tells you about how much charge can be, Yep. I don't know why. That should fix it. Yep. Okay. So coming back to the definition of capacitance, being the ratio of the total charge of the system to the electric potential difference across it. What we really want in defining this is it's some measure of, for some difference in electric potential that I want put between these, how much charge can I put on that system? And so really this all kind of carries over from the things that we've done with Gauss's law, and it's just adding one extra step. So this delta V, like I was alluding to earlier, is the same delta V that we were calculating when we were applying Gauss's law. And the extra step to calculating capacitance is really just to find what delta V is, and then take the ratio of the charge to delta V. So let's see how this works. And the other thing that I talked about in the notes is capacitors are springs, and not really in a literal sense, but they behave physically like springs do. And we'll see that even more when we talk about Faraday's law and the equation of motion for charges in a circuit. But for now, the way that we can see this is if we consider we want to add charge to this system, and doing this incrementally by continually adding some amount dq. And we'd like to say, how does the potential energy change as I do this, or what is the potential energy that can be stored in this capacitor? So we know that in general the relationship between the electric potential and the potential energy is just that U is equal to Q times V. And so if we want to do this in terms of some infinitesimals, that is to say that du is equal to dq times V. And to find what the total potential energy is, we just need to integrate both sides. And this side is telling you I'm integrating over the charge that I'm adding as I'm doing this. Now, V can actually be written in terms of the capacitance. So that's to say that V is going to be equal to Q divided by C. And so this is going to be dq Q divided by C. And now when I integrate this is going to give me a 1/2 Q squared divided by C. Okay. And this is the potential energy of a capacitor. Okay. Now, what this looks very similar to actually is the potential energy of a spring. And we can see that by starting at what is the force of a spring. This is going to be minus kx, x hat. U is going to be equal to the negative integral of f dot dr. And so this is going to be equal to the negative integral of kx dx, which is going to be equal to 1/2 kx squared. Okay. So you see, between the two of these equations, you have this 1/2 constant factor out front, and then we have something squared. So in this case, it's charge squared. In this case, it's the position squared. So when we're thinking about what capacitors do in electronic systems, it's a lot like a spring. So a spring, if I compress it, it's storing potential energy. Capacitor, when I put charge on it and I force that charge to stay there before where I close some switch. That's also storing energy that can be, as the charge leaves the capacitor, it's able to do work in the same way that as the spring restores back to its natural unstretched length, it's doing work. Okay. So now that we kind of understand conceptually what capacitors do and how they're defined, let's talk about how we can calculate what the capacitance actually is for some particular geometry. And the example that I did here in the notes was the parallel plate capacitor. And so that's to say, if I have some area A here, and this is separated by some distance of L, we want to find what the capacitance of this system is if I put some charge plus Q here, some minus Q over here. Okay. So looking at our capacitance equation, we already have Q. That's just going to be the Q that we have here. But we need to figure out what delta V is. So in order to find what delta V is, we go back to Gauss's law and we find what the electric field is. So Gauss's law, as always, integral E dot ds is equal to Qn divided by epsilon naught. And I'm going to make an approximation here to say that these plates are close enough together so that the electric field is always in this direction. It's not really. It would bend something like this, but I'm making that approximation because I want to use Gauss's law, and it would be very hard if this was bending like this. Okay. So the way I'm going to draw my Gaussian surface is going to enclose the entire thing, the entire surface area, and then come out over like this. Okay. And the reason why I do that is because if this is a conductor, the flux through the surface that's on the inside of the conductor is 0 because the electric field inside the conductor is 0. The flux through the sides is going to be 0 because the electric field is going to be perpendicular to that dA vector. And so the only flux that I'm going to have is through this surface right here. And that surface has some total area A because I'm enclosing the entire face of this. And so this says that the left-hand side of Gauss's law is just going to be E times A. Now, the Qn divided by epsilon naught, this one is pretty easy. This is just going to be Q divided by epsilon naught because I'm enclosing the total charge. Okay. So I can rearrange this, and this says that E is going to be equal to Q divided by A epsilon naught. Say this is some x-hat direction. And now what we want to do is we want to find delta V between here and here. Okay. So this is going to say this is equal to the negative integral from 0 to L of E vector dot dl. This is going to be equal to minus Q divided by A epsilon naught, integral from A to L dx. And so this is minus Q divided by A epsilon naught L. Okay. Now we're one step away from finding the capacitance. We have what delta V is. And so we just take this and we plug it into the definition of capacitance. And that's going to say that the capacitance is going to be equal to A epsilon naught divided by L. Okay. And so this is kind of an interesting result because what it tells us is that the larger the plates, the more capacitance. The smaller the distance between these, the larger the capacitance. And then we have this permittivity of free space that's coming along for the ride here. What we did here was we assumed that this is a vacuum here, but we could also put some material in between here, like a piece of plexiglass or some other insulating material. And that would also change what the capacitance is. So this is the derivation of something that you might have seen in high school or in a previous physics class. But this is kind of a jumping off point for a couple of other problems that we can do in calculating capacitance. So rather than having one plate, I could have put a second plate here. Well, how do I draw I can put a second plate here, right? And then, if I want to find what the capacitance is across the entire system, I would just integrate this rather from 0 to L. The electric field here would be the same if this was neutral. So I have minus Q here, a plus Q here. Then I have I integrate this twice, and the reason why this is kind of interesting to think about if I add more plates here is this is how we get at the equations that you might have just memorized or were told to you for how capacitors add in series and parallel. So this would be an example of capacitors in series, and so what you can show, and I'll probably have this as something we'll do in class tomorrow, that 1 over C1 plus 1 over C2 is equal to 1 over the equivalent capacitance. We'll talk more about this in class tomorrow, but that's something that you can do here. You could also show how adding capacitors in parallel works by doing something similar. So rather than having this as a sequence like this, I can have another set of plates like here and here, and if I put both of these systems at the same electric potential difference or the same voltage, then I could run through these calculations and I would see that I would get the same thing for the equation for adding capacitors in parallel. So this would be in series. And then in parallel, we have CEQ is equal to C1 plus C2. Like I said, you might have seen these equations, but per usual, I don't like just citing things. I like proving them and having you guys go through the calculations to see why they're true. These are some things that we'll be doing tomorrow and Thursday. The other thing that we could do is we considered parallel plates here, but we have two other symmetries that we can play with when it comes to Gauss's law, and that's the spherical symmetry and the cylindrical symmetry. And again, we could play the same games with series and parallel with cylindrical and spherical symmetry. So to give you some idea, I'm not going to solve this one because I do want you guys to think about this for the homework. The second question that I asked, or the last question on the homework, said, that's a terrible circle. If I have some conductor that has some radius A, thickness T, surrounded by another conductor, inner radius B and thickness T, and I put some charge Q at the center, on the center shell, what is the capacitance of this? And really, it follows exactly the same process that we went through for the parallel plates. The only difference is, because of the symmetry, we're going to have a different Gaussian surface that we're going to draw here. We draw some Gaussian spheres instead of the Gaussian cylinder that I used over here. But that one I'm going to leave for you guys to think about for the homework, and we'll talk more about that one tomorrow in class. Okay. Any questions about this stuff? Let's see how am I on time? I got 6 minutes. If there are any other questions. Okay, well, if that's it, I'll sign off and let you guys work on this homework problem, and I'll see you tomorrow in class. Oh, we got one more. Okay. So for any given geometry, when using Gauss's law, we can just say that the surface area is A, or do we have to calculate it if it's different on a variable such as a radius of sphere? Yes. Yes. So the thing about the sphere is you're absolutely right. You need to say specifically what the area is, right? So you could say add some area A, but if we know that this is a sphere, we know that the area is 4 pi r squared, right? So that's really the difference between the two examples. So on this one, when I evaluated the left-hand side of Gauss's law, it was E times A. For this one, it's going to be E times 4 pi r squared, right? that's also going to change our calculation for the difference in electric potential, right? Because for this one, the electric field actually was just a constant, right? It was always just pointing to the right, and it had the same value moving outward. But for this one, the electric field is going to vary as the radius. So when I calculate the difference in electric potential, because that's what I need to find the capacitance, it's not going to be a constant. And it's ultimately going to be dependent on this radius that we have that's part of the left-hand side of Gauss's law after I evaluate it. So let me see that I answer that. Let's try to give geometry when using Gauss's law. Calculated yeah. So I think that should answer your question. Yeah, A needs to be parameterized in terms of the symmetry that you have, and spherical symmetry, it's going to be 4 pi r squared. And like I said, that'll be important for doing this calculation. Okay, any other questions? I could. How does the thickness of the shells play into the limits of integration? I don't want to answer that. I don't want to answer that. Think about what it is that I'm doing when I'm calculating the integral. I'm not going to hold out on you forever. I'll answer this more tomorrow. But think about what it is that I'm doing here in defining what E is for different regions and defining what the limits of integration are. Those two are going to be related to each other. And the other thing that you want to take into consideration is the fact that inside the conductor the electric field is 0. That's all I'm going to give you for right now. I do want you to work through this without too much more direction from me. But the limits of integration are important, and as always, it has to do with where am I starting and where am I ending for each portion of the electric field. Okay. I'll answer that question more completely tomorrow. Okay. Other questions? Other questions?